and then we're left with a torical on this lattice. And then we just use the upper bound and lower bound technique and hope that we can match these two bounds. Okay, so this is the strategy. But let me give you more detail. I mentioned the control NOT gate. This is the exact definition of control NOT gate. So this is the control qubit. If it's 0, then you do nothing. You do identity to the target gate. If it's 1, then you perform the sigma x operator to the target gate. You can show that under conjugation of these control NOT operation, the identity on the control and z on the target will be mapped to z cross z. And z cross identity remains the same, and I times x would remain the same, but x times I would give you an additional x. So maybe let me illustrate what this means. Suppose you have a torical and plaquette operator z1, z2 up to z5. This is described as plaquette. And you attach a 0 spin, and you apply the control NOT operator from 2 to 0 and 1 to 0. According to this rule, this 0 is the target. So 0 is the target, and 0 is also eigenstate of sigma z operator. So the target with z operator would transform to a z tensor product z. So this would pull out additional z1 and z2. So this means that you can actually separate these 5 product z operator into 2 terms. One is from this plaquette, the other is from that plaquette. Okay. So this actually is a mapping from this torical to that torical. You can do the reverse, then this would map this torical to that torical on this particular plaquette. So therefore, that justifies the graphical rule that we have here. So you could also do this for the vertices. On the vertices, you attach a plus state and apply control NOT to these two. In some sense, this would create an additional edge. If you reverse the process, then it's basically shrinking the edge. So in terms of graphic, if you think of the reverse way, this is how you remove a single edge. And here is how you remove one face. Okay, and according to these rules, you can verify that because the x is eigenstate of sigma x, under the conjugation of control NOT, it would generate additional x1 and x5. That justifies the product of star operator. This star operator is actually can be split into x0, x1 here, x5, plus these vertex operators, x0, x2, x3, x4. Okay. So basically, I just justify the graphical rule. So in terms of this, then you can think this graphically. What you do is you apply the 2 rules that I have. I can remove edges. And then I could also contract the edges. Then it becomes the torical here will become a torical here. So then you can do the geometric entanglement on this coarse grain lattice. And I've just described you how to do that. You find the upper bound using really product state on this transformed torical. And then you also need to find the lower bound. The lower bound is for the bipartition geometric entanglement. And it turns out you can just use a simple bipartition, and that would enable you to actually match the lower bound. Okay, so I want to maybe give some remark here. For infinite system, you can imagine you do this coarse graining process, and because your system size is infinite, you can actually map the torical back to the same torical. So therefore, the torical is a fixed point wave function. In some sense, this justifies that there is existence of long-range entanglement, because you cannot remove, by removing just short-range entanglement, you cannot remove the torical to a product state. If you have finite system, for example, on the torus, you can actually coarse grain everything so that you are left with two spins. And these two spins are effectively what I described, the effective two spin, two qubits. I want to also remark that you could also do this coarse graining for the quantum double model and then compute the geometric entanglement. The coarse graining was also done in StringNet, Vidal and coworker. So the upshot of what I have just calculated is that the geometric entanglement has this boundary law proportional to the boundary of the block size and has an edited constant. And this actually is the same as the topological entanglement entropy. And we verify this for a few Pictorial wave function, torical, double Samuel, quantum double model. We have not verified generic for the StringNet yet. So I want to contrast, this is the area law for the entanglement entropy. You have a bipartition, and in entanglement will be proportional to the boundary of the subsystem. But for the geometric entanglement, you need to consider many blocks, and there is a bulk law because entanglement would scale with the number of blocks, which is indicated here, but also scale with the number of system size. And there's a constant term that you may be able to extract from fitting the scaling, either fitting to the boundary size or fitting to the number of blocks. Okay, so the intuition that I actually described is doing these graphical rule is actually we want to coarse grain to remove short range entanglement. This means that to remove the star operator inside the block, so that the star operator can only exist at the boundary. And this is the reason why there's a boundary law. Okay, and this also works for quantum double model. Okay, any questions so far?
Is there a generalization to three-dimensional system?
Three-dimension, if you generate the torical naively, then I believe you could also do this. But then the block will be a cube, for example, of certain size. Yes?
Yeah, you use geometrical, you can actually require the gap also to be very large. You have a bipartition, but there is also gap into shading the area.
You mean the gap, not in terms of spectrum, right? The gap in. Oh, you mean the system? Yeah, you don't need.
You know, there's an IO. Does IO also refer to the gap in the lower?
Oh, there's no gap. Actually, there's no gap between these. That's just schematically. So the spin here.
There's no gap.
The spin here is next to each other. Yeah. So there's no gap in the region. So each spin has to participate, or each block has to participate. What we don't have is a field theoretical argument that this would hold generically. But if someone knows how to do that, I would be very happy to discuss with. Okay, how much time? 20 minutes?
21.
21, okay. Okay, so to go beyond the torical and to test the idea of whether the scaling will help you to identify the topological entanglement entropy, we want to go beyond that, beyond torical, so that actually the wave function is deformed so that the correlation length can actually be large. Can also be arbitrarily large, close to transition. Because in that case, if you want to compute the entanglement entropy using various combination of partition to extract the topological part, it may not be doable because the size may not be bigger than the correlation length. Okay, so this comes to the second part. So what do I mean by deforming the torical? What I mean is that for each site, I want to add a different weight to my wave function. For the 0, I get a weight 1 plus g. For the 1, I just have 1. I do this for all the lattice sites. So you can imagine that g is some sense penalized large loops. So when g equal to 0, there's no penalty. So therefore, and we also know that this is the torical ground state. This is what we start with. If you start increasing g, you will penalize large loops of 1. And at the end of infinite limit of g, this will become a product state. So we have just written down a wave function that continuously connects from torical to a product state. But apparently these are two different limits. One is a topological phase. The other product state is a trivial phase. So writing down this wave function, somewhere there must be a phase transition. So we want to test whether we could use this topological geometric entanglement to extract these constant terms and show that actually is constant inside the topological phase and drop to 0 in the trivial phase, and whether we could also use this to identify the transition point. So we want to test this. So maybe I should actually give you this pictorial understanding. The ground state wave function is product of these loop configuration. Applying these string tension parameterized by the G, we actually frustrate large loop because a loop, larger loop have more number of spin, and this would get lower weight. The 0 would get larger weight. So the weight suppression is this constant raised to the parameter. Okay, so what we did, because for this wave function, we don't know yet how to compute analytically the geometric entanglement. So we turn to numerical method. So we choose, the way we do the partition is we choose this, somehow this zigzag partition. Because this is not on because the spin are not on vertices, on the edges. So we choose these somehow like a zigzag, and this another zigzag, etc. So we'll call this one block, another block, and etc. So this is the length, and this is the number of blocks. And we simply take this as ansatz, because we have seen that for various ground state, this works at fixed point. So we assume that this would hold, and so the entanglement, the geometric entanglement, would be proportional to the product of number of blocks and the length, and then would have an edited constant. So the goal is to extract this edited constant and to see whether we can identify a transition. So the method that we use is the Tensor-network method, or tensor product state. Jensen mentioned that earlier in the morning. So this is upshot of the method. So we have a wave function. What we want to do is to write down this as contraction of tensor network. And the way we choose our blocks is we choose a ring of spins. So it's a product state of chains, and for each chain, you could also use matrix product state to approximate that. And as I said, to get the closest product state, you don't need to do iteration. So we can also apply that to the tensor network to iterate and then get the maximum of product state, the optimal product state. From there, we can get the entanglement. So, but how do I write down the tensor network for the torical ground state? For general string net, because torical is one special case of of StreetNet has been, there have been 2 papers describing how to write down those. So I'll refer to you the general method. For the torical, there's a simpler way to write it down. So maybe I'll briefly describe that. Because our wave function, this particular one is sum of the group element applying to the 0 product state. You could actually write, if you simply ignore these constraints that product A become 1 because you're not interested with the normalization. So you could just write as product of these. And so there are 2 types of operator. One is the identity. So this one is identity here, here, here. The other is actually applying an actual AV operator with product of sigma x. So you could assign an internal indices that connect these operators. For example, if I assign some internal index, 1 to be linking all these identity here, and 2 I can link these x operator. So to get the torical tensor network description, what you simply take is just insert a 0. This is what you start with. For each edge, you have a 0, and then inserting to that, there could be 2 star operator acting on one edge. So for this edge, there's a star operator here, there's a star operator there. So this describes the action from the right, this describes the action from the left. And to get, for example, if you want to get what is the tensor for the one physical 0 state, then you just think of how you can get from 0, maybe with identity still 0, and then another identity to 1, or you could have the other possibility, 0 is flipped to 1 and flipped back to 0. So analyzing that, you get a tensor. So for those who are working with tensor product state, these dashed line are the internal indices, the black line is the physical index. Okay, so this is just for those who are working on the tensor product. So these are the tensors. These are the non-zero tensor in this ground state. So if you put this tensor on the 2-dimensional network, then this describes the torical wave function. I only show you that this is one ground state, but you could also apply the string operator at the virtual level, and you can actually get all the other 3 ground states. So what we want to do is we want to deform the torical from this tensor by giving more weight to 0. So essentially, you just change 1 to 1 plus g here, and these 2 remain the same. So this describes the tensor on the horizontal edge. The tensor on the vertical edge is rotated by 90 degrees. Okay, so if you have the tensor network description, and you can also write the product wave function and go through the iteration process, you get the closest product state, and then you plug in and evaluate the overlap, and you get the geometric entanglement. So this is the process. Okay, so let me show you the result. So imagine we're sitting at g equal to 0.0. When g equals 0, this is a torical. That's sitting at g equal to 0.4. And what we did here, we plotted geometric entanglement as function of the linear size and the number of blocks. So you see that as block size increases, we get better and better extrapolation to the -1. Even for moderate size number of blocks, this works very well. And we get -1 for 0.4. So this means that this still is in the same topological phase as the torical. And what if we look at g equal to 0.6? We get extrapolation to 0. So this must be the same as the product state. So this is the result. So we extrapolate to large number of blocks and large number of lengths. This is the topological geometric entanglement. It's stage 1 because we're using log 2 basis, so it's stage 1 from torical up to some value of the string tension and drop sharply to 0 and stay 0. So from this, we will infer that this is a topological phase, similar to torical in the same topological phase. And this is the polarized phase. So we identify there's a transition here around 0.56. This is actually the raw data that you can see that it's very sharp if you have if your number of blocks is large. This is 100, and for small number of blocks, you get some finite size effect. But we can focus on large size number here. Okay, so how do we know that this is correct? Yes.
So here, the product you choose is kind of very long.
Ring. Yeah, long ring because I'm
yeah,
toric.
but
The other
direction.
direction.
You have this more finite size in both directions.
Yeah.
So these two different choice of products, they give you different results or how?
We try also increase the width of the ring.
So suppose it's not ring, it's just suppose it's the product is the block size.
Oh,
fine
okay.
In both
Yeah.
directions.
We have not done that because it's just technical reason, because it's easy to write down a metric product state. If you want to do what you just described or use the same picture that I just have been describing in the beginning, use a square block size, we have to parameterize the product state using a tensor product state.
But the concern is that the two choice product state may give you different entanglement entropy in the way you define.
Yeah. So we verify that it's the same on the torical point. Yeah. And then you have the ring. Yeah. So next question is, how do we know this is a correct number? But I also want to mention that here there's a transition, so that means the correlation length is really large. But we get the correct result. I'll show you that's the correct transition point, even though the ring, the width is only of width 1. It's much smaller than the correlation length. So how do we know it's correct? In fact, you can map this wave function, the norm of the wave function, to contraction of tensor network. So remember I just described to you that there's a tensor, maybe I just here. This is my torical tensor. If I want to compute the wave function, I need to supply the other one and contract the physical dimension. And I get a double tensor. T. It turns out that you can actually map these double tensor, T, to the tensor that describes the partition function of classical Ising model. So this is the tensor we found. And it can be mapped to Ising model, and the mapping is via these relations. So beta is inverse temperature, J is the coupling in the Ising model. So by mapping this to a classical model, and by knowing the exact value of the Ising transition, we can infer the transition for the torical, deformed torical. And we get the exact number is very close to the numerical number. Okay, so using entanglement, we have located a phase transition from the topological phase.
So
Yes?
that's a 2D Ising transition or 3D Ising?
2D Ising, classical Ising. Because the wave function, we only concerned about the ground state wave function, the normal wave function, not the Hamiltonian. If you map the Hamiltonian, you have to map a 3-dimensional. Yeah. So using the entanglement, we have located phase transition. But as I said earlier, one quantity is not enough to characterize what kind of topological basis. So surprisingly, entanglement can be used smartly to extract further information. I'll leave this to tomorrow. And I would also describe the quantum computation using AKLT, but it's a very different subject from this, as requested by the organizer. Okay, so I'll stop here and welcome question here. Thank you very much.
Is there any questions from the audience?
Yeah, can this be extended to the symmetry protected topological phases, maybe by imposing symmetry on the product state?
I have not thought about that aspect, but it's possible. Yeah, I think it's possible.
Any other question?
But maybe let me point out there's a work by Xiaogang that they use a tensor gauge symmetry preserved tensor renormalization method, and they have a different way of deforming the torical. I think it's from torical and also double semium, and they could actually use modular matrices to identify the transition. And in fact, Jingyu actually used this wave function and carry out Xiaogang's method and also get the same transition form. So therefore it might be possible, but I would say maybe it's better framed in Xiaogang's framework using the tensor gauge symmetry protective way of doing the RG.
We still have 2 or 3 minutes, so you can still have questions. Okay.
Thank you.
If no question, we can thank the speaker again. So the next will be start at 15 minutes later.